In this video, we're going to look at how signals move through an IQ transmitter and receiver to demystify the behavior of IQ transceivers. This slide shows an IQ transmitter and an IQ receiver. I've drawn some example I and Q signals on the left, and the LO that they'll be multiplied by appears next to the mixers. When we carry out the convolution with the LO, we wind up with slightly different spectra from the I and Q paths. The spectrum on the I path is purely real, and it's an even and positive spectrum because the I signal was convolved with a cosine. Both signals in the I spectrum have been reduced by a factor of 2 relative to the input because the cosine splits its power into the upper and lower impulses. The Q path is purely imaginary, and it's an odd spectrum because the input was convolved with a sine, but it also has been reduced by a factor of 2 in size. These signals are added together in the air, and because the I path is purely real while the Q path is purely imaginary, the two paths don't affect one another. It's often said that the I and Q signals are orthogonal because of this property. As a result, the phase rotator is an extremely important part of the transmitter because it's responsible for preserving this orthogonality property. If the LO signals aren't exactly in quadrature, which is to say 90 degrees out of phase, then some I will leak into Q and vice versa. Similarly, the phase match on the I and Q paths of the receiver matters a lot to preserve this orthogonality. When the I and Q paths don't have the same phase at the receiver, it causes the received constellation to rotate, which naturally causes difficulties for decoding the information coming out of the I and Q paths. Finally, the transmitted signal is received and multiplied by a sine and a cosine again. This figure is ignoring the delay introduced by the propagation of the wave between the transmitter and the receiver, but you could imagine it's there by multiplying every term on the receiver side by e to the minus 2 pi jr over lambda. The result of multiplying the received signal by a cosine is a half-sized I signal with an image signal, and a Q signal that interferes destructively at baseband to cancel out completely, plus again some quarter-sized image signals. So if you were to low pass this I path, you'd recover only the Q signal, only the half-sized Q signal. The Q path has the opposite result. The I signal interferes destructively at baseband and cancels out, while the Q signal is reconstructed at baseband, and you're still left with these quarter-sized image signals that you need to filter out. So in summary, IQ receivers aren't black magic. The I and the Q components in the spectrum cancel in the received signal. And finally, the IQ phase and gain balance and having a correct phase for our synchronous demodulation are very important in IQ transceivers.